Okay guys, we're going to start the next series of videos here dealing with thermodynamics. In this first video, what we're going to do is review some of the content from Chem 120 that's needed in order to understand the new material. So this one is all review. The subject of thermodynamics involves the study of the relationship between heat and other forms of energy. We are interested in chemical thermodynamics, which further focuses on the energy that accompanies chemical reactions. And so the types of questions that we're interested in are, what is the energy change associated with the chemical reaction? How much heat will be generated or absorbed as the chemical reaction occurs? That's going to be the subject of the review. And then these other questions here: will the reaction occur on its own? And if so, will it generate a significant amount of product? These are the new types of questions that we'll ask. And as you can tell, they're somewhat related to the topic of equilibrium. And so the goal of this chapter, after the review, is to link thermodynamics with the things that we've been learning about for chemical equilibrium. So we'll kick off the review here with some basic definitions in thermodynamics. We tend to use generic, perhaps even abstract terms when talking about thermodynamics, and so this slide is meant to review some of those terms so that we're all on the same page. Very often when discussing thermodynamics, we refer to the system or the system of interest. That simply refers to the part of the whole universe that you're interested in. So whatever it is you're studying. In chemistry, almost always we're studying some type of chemical reaction mixture. And so that will be pretty much our system of interest. The term surroundings refers to anything else in the universe, anything outside of our system. And so we'll come across these terms in both the review and in the new material. The objective of thermodynamics is to characterize the state of the system. And in thermodynamics, one defines the state of the system by specifying the different variables that describe the system. And it turns out in thermodynamics, you need only 4 variables to describe the state of a system. You need to know the pressure, the volume, the number of moles in the system, and the temperature of the system. That's at least for a pure component system. So if you have just one type of compound in the system, you only need 4 variables to describe it. And you've seen examples of these variables in action. For example, when you studied gases in Chem 120, you worked with the ideal gas law. Here we can give it its true name, the ideal gas equation of state. That is, a given thermodynamic state of an ideal gas satisfies this equation of state, which you see links the different thermodynamic variables together. Thermodynamic variables can be characterized as either extensive variables or intensive variables. Extensive variables depend upon the size of the system. So for example, the number of moles of a gas depends on how much gas you have. And so if you doubled the size of your system, you would end up doubling the number of moles of gas in the system. Likewise, volume, if you think about the volume of a gas, if you doubled the size of your system, you would end up doubling the volume of the gas as well. So number of moles and volume of gas are examples of extensive variables. Intensive variables, on the other hand, are independent of the size of the system. And the way I like to remember that is by using the IN in the word intensive and the IN in the word independent. Examples of independent variables, of intensive variables, are the temperature of a sample as well as its pressure. One thing that I wanted to note, if you take the ratio of 2 extensive variables, the result is an intensive variable. So for example, consider the mass of a sample. Mass is another extensive variable. If you double the size of your system, you will double its mass. If you take the mass and divide it by the number of moles, you get the molar mass. And the molar mass is independent of the size of the system. For example, if you had a sample of water, it has a molar mass of 18 grams per mole. And then if you doubled the amount of water you have, you would increase its mass and its volume and the number of moles, but you wouldn't increase the molar mass of water. And that's what the term molar means. Molar means you take a extensive quantity and divide it by the number of moles of substance, and the result is an intensive quantity. So the ratio of two extensive quantities is an intensive quantity. Another example would be the density of a sample. For example, density is mass divided by volume. Both mass and volume are extensive. However, the density of a substance does not depend on the size of the system. The density is an intensive quantity. We will have all sorts of molar terms as we explore thermodynamics. Another way of characterizing quantities in thermodynamics is by designating them a state function or a path function. State functions are properties of the system, for example, the variables that we've looked at. They depend on the state of the system, and they are considered a property of the system. Path functions, on the other hand, are not system properties. They do not depend on the state of the system. In fact, they only are detected when the state of the system changes. They are associated with the path between two states. So examples of state functions, we've already seen a few: pressure, volume, number of moles, temperature. In a moment or two, we will look at the internal energy of a system. That is another state function. A little bit later, we'll look at the enthalpy of a system, H. That's a state function. And in the coming videos, we'll also talk about entropy and Gibbs energy. These are also state functions of a system. One thing about state functions, since they only depend upon the state of the system, you can calculate the change in a state function by taking the value of the state function at the final state minus the value of the state function at the initial state. And we use this notation delta to represent a change in a state function. So the change in pressure would be the pressure of the final state 2 minus the pressure of the initial state 1. You can do this for any of the state functions listed here. Path functions are quite different. They are not system properties. They depend on the path between states. There are two path functions. One is called work, represented by lowercase w. The other is called heat, represented by lowercase q. Because work and heat are not state functions, it would be incorrect to use the notation w subscript 1 or q subscript 1, because that would indicate that work or heat was a property of state 1, which is not true. Likewise, you would never use the delta for work or the delta for q, because it would imply this type of definition, which is not true for path functions. Well, we'll talk about internal energy next. Internal energy is a extensive thermodynamic state function. Okay, so the internal energy is a property of the system. It's measured in units of joules, or more commonly kilojoules in chemistry. It represents the sum of the kinetic and potential energies of all of the particles within the system. Just to give a quick review of that, in case you're unfamiliar with these terms, kinetic energy is energy associated with the particle's velocity, so it's an energy of motion, whereas potential energy is the energy of interaction between particles. So, for example, if you have ions, or if you have electrons within molecules, and there are protons and within the chemical system, there's all sorts of electrostatic interactions between molecules, and so those types of interactions are potential energy interactions. They are associated with the distance between different molecules. So their potential energy is an energy associated with the position of a particle. Anyway, the sum of the two for every particle or molecule in the system equals the internal energy of the system. And in the next line, I want to distinguish the internal energy from other types of energies. So, for example, you might think about the total energy of a system. Let's suppose that we've got a chemical reaction mixture, and as you're sitting in your lab doing your chemical reaction, the Earth is turning around, so there's a kinetic energy associated with the fact that the Earth is in motion and it's revolving around the sun. So technically, the chemical reaction mixture has a overall kinetic energy associated with the motion of the entire system. Likewise, if you're doing your chemical reaction on the 4th floor of the science building, it has one type of potential energy, the potential energy of being up high, versus if you're on the ground floor, it would have a lower potential energy associated with its position relative to the center of the Earth. These types of energies, the overall kinetic energy of the system and the overall potential energy of the system, these are not of interest in chemistry. We don't really care about those. What we care about is the energy inside the system, how the particles are moving relative to one another. What are the interactions between the particles? All of that stuff is wrapped up in this internal energy term, and that's what we care about as chemists. Well, when you have a chemical reaction, you go from one state to another, and so a change in the internal energy of the system can be conceptually calculated by taking the internal energy of the final state minus the internal energy of the initial state. In practice, you never get to use this formula because you can't go out and measure the internal energy of a system. You have to calculate it in other ways by measuring heat flow. And that's what we'll look at in one of the upcoming slides. But anyway, internal energy is a state function, and at least in principle, it can be calculated in this way. Changes in internal energy come about through two different ways. You can either do work on your system, or you can heat the system. Okay, so a change in the internal energy is brought about by either doing work or by heating. The internal energy of the system can increase, in which case we say that the system has absorbed energy, or the internal energy of the system can decrease, the negative sign, and we would say that the system evolves energy. The first law of thermodynamics involves the internal energy, and it states that the total energy of a system plus its surroundings is a constant. Okay? This is also called the law of conservation of energy, and it tells us that the total change or the internal energy change of the total system plus surroundings must be zero, such that the total energy is a constant. And by taking this second half of the equation and rearranging it, we can say that the system energy would be equal and opposite the surroundings energy. So in that sense, energy is neither created nor destroyed. If the system gains energy, that energy would be lost by the surroundings. Or if the system loses energy, then the surroundings would gain that energy back. You can't create or destroy energy. So the total amount of internal energy is fixed. A little bit of the notation here. The reason why I've written system in parentheses is by convention we do not include the subscript SYS when referring to the internal energy change of the system. So when there's no subscript, as we have here, we should automatically regard this as being the internal energy change of the system. However, when you're talking about the surroundings energy change, you do include the subscript. Well, as I mentioned on the last slide, there are two ways in which you can change the system's energy, either by heat or by work. And so this is another expression of the first law of thermodynamics. Let's talk about work and then heat. Work is a type of, well, first it's a path function. Okay, it's also measured in units of energy, so joules or kilojoules. And it's an energy transfer. That's the key thing. It's a transfer of energy. And for work, that transfer of energy is associated with a difference in force between the system and the surroundings. And whenever you have a difference in force, something is going to move. So we often think in terms of a piston, so a gas, a compressed gas inside of a piston. If the force of the gas acting on the piston is larger than the force acting outside on the piston, what's going to happen is that piston is going to expand. There's some important sign conventions at work here. When the work is greater than zero, that means that the system gains energy. So we say that the surroundings does work on the system. So energy is transferred from the surroundings to the system when work is positive. Conversely, if work is negative, that means that the system loses energy, and we say that the system does work on the surroundings. The most common type of work that you encounter in basic thermochemistry is called PV work. And this is what I was talking about with respect to a compressed gas in a piston. PV work is the work that you get when a gas expands or is compressed. And if the external pressure acting on the system is a constant, the work can be easily calculated using this formula. We're not going to use this in any of our problem solving. It's not something that you're going to need on the assessment. However, it is used in some upcoming slides to explain enthalpy. So anyway, this is the expression for calculating the work when a gas expands or is compressed, that is when its volume changes, against a constant external pressure. And the negative sign is for the sake of these conventions that we want to follow. We'll talk about heat next. Heat is another path function. It's the other path function, I should say. It's measured in units of energy, so joules or kilojoules. And it is also an energy transfer, but instead of being an energy transfer associated with a difference in force, it's an energy transfer associated with a temperature difference. So whenever there's a temperature difference between the system and the surroundings, you will have heat flow. Here are the sign conventions for heat. They're similar to those for work. When heat is greater than zero, that means that the system gains energy from the surroundings. We call that an endothermic process. When heat is negative, that means that the system loses energy, and we call that an exothermic process. A formula that you've worked with previously involving heat is this one here. The amount of heat associated with a particular temperature change of a material system is proportional to the mass and the so-called specific heat S of the sample. And so the specific heat is a property of a given material, and then the mass is, well, the amount of mass in the sample. And so this is a formula that you've worked with previously. We're really not going to make any use out of it in this particular course, although you have done some problem solving with it in the past. We are interested in the heat flow associated with the chemical reaction. Okay, here are some examples. For an endothermic reaction, okay, the heat is positive, and here's an example. Here we've got this barium hydroxide hydrate reacting with another solid, ammonium nitrate. When you mix these two solids together, you'll form these products, and the system will, or the surroundings rather, will get colder. That is, the chemical reaction is going to absorb thermal energy from the surroundings, and that's going to increase the energy of the system. Conversely, here we have a combustion reaction. So this is a combustion reaction involving the burning of methane. This is an exothermic process, and as you know, when you burn fuel, thermal energy is produced, and so we get a negative heat for that. Let me draw your attention to this first bullet point. When you have a chemical reaction occurring under constant volume conditions, the change in the volume is, of course, zero, right? That's what constant volume means. As a consequence of that, the PV work that's done will be zero, right? Because the PV work is related to delta V, and if delta V is zero, then there's no work done. And if we take that first law expression and rearrange it and solve for the heat, we get heat equals delta U minus W. In this particular case, W is zero, and so we find that the heat equals the change in internal energy. So if you're carrying out a chemical reaction under constant volume conditions, and you measure the heat flow associated with that chemical reaction, it's a direct measure of delta U. Okay, and so that's one way you can experimentally determine delta U, by measuring heat under constant volume conditions. There's an experimental technique called bomb calorimetry, which does exactly that. In many situations, however, you don't have constant volume conditions. Instead, you have constant pressure conditions. For example, if your chemical reaction is open to the atmosphere, the external pressure will be constant, but the volume won't necessarily be constant. And so in this case, when you go to determine what the heat is using the delta U minus W expression, you will actually have some PV work, which I've substituted in here. And so this thing is no longer just delta U, it's delta U plus this P delta V term. Okay, so when you measure the heat, you're not directly measuring delta U, you're measuring something else. And that something else is what we call the enthalpy change for the reaction, delta H. Enthalpy, H, is another state function. It's an extensive property of our system. It's measured in units of energy, joules or kilojoules, and this is its formal thermodynamic definition. It's equal to the internal energy of the system plus the value of pressure times V for the system. And the reason that it's useful is because under constant pressure conditions, when you measure heat, it's equal to delta U, it's equal to delta H. And that's why we have enthalpy. The reason why so much of thermochemistry is centered around delta H is because most chemical reactions are carried out under constant pressure conditions, and it's more convenient to work with delta H than it is to work with delta U. And so that's what we do. For chemical reactions, the heat of reaction under constant pressure conditions is called the enthalpy of reaction, delta H, with a little subscript R next to the delta. We often see the enthalpy of reaction expressed next to the chemical reaction of interest. These are called thermochemical equations. They're a little bit different than stoichiometric equations, right? In a stoichiometric equation, we always get rid of the fractions in the stoichiometric coefficients. That's something that we made you do in Chem 120. But for a thermochemical equation, the fractions are allowed. And that's because we don't interpret the thermochemical equations at the molecular level. In a stoichiometric equation, like this one here, we need to get rid of all of the fractions because it wouldn't make sense to have half a hydrogen molecule. In the thermochemical equations, we don't interpret the stoichiometric coefficients at the molecular level. We always interpret them at the macroscopic level, at the mole level, and it's okay to have half a mole. And so that's one distinction between stoichiometric coefficients and thermochemical between stoichiometric equations and thermochemical equations. Phases are very important in thermochemical equations. So here I've got two reactions. They look almost the same, but the difference is in one we're making water vapor, in the other we're making liquid water. And these two reactions will have different enthalpies of reaction, as you can see here. So you have to pay attention to the phases in your thermochemical equations. We'll also be doing some algebraic manipulation of thermochemical equations in this review. And here what I've laid out are the rules for thermochemical algebra. If you take a chemical equation, a thermochemical equation, and you multiply the equation by a factor, such as we've done here, we've taken this thermochemical equation and we've divided it by 2 to get this thermochemical equation. You do the exact same thing to the delta H value. So here we have the delta H for this first equation. We divide the equation by 2, and we do the exact same thing to delta H. Also, if you take a thermochemical equation and you reverse it, that is, if you take the reactants and make them products and the products and make them reactants, that's equivalent to multiplying the chemical equation by -1, and you do the exact same thing to delta H. So if you reverse the chemical equation, you need to change the sign of the delta H that accompanies it. And if you add and subtract chemical equations together, as we'll see in some of the examples, you do the exact same thing with delta H. So in this first example, we'll explore using those rules. In this case, we've got a thermochemical equation. We're making liquid water. Here's its delta H value. We're being asked to write this equation for 1 mole of liquid water. So we'll take this equation and we'll divide it by 2. That gives us this one. And we do the exact same thing to the delta H value. So I've taken this delta H divided by 2 to give me this -286. In the follow-up, what they want us to do is to take this second equation that we have on the slide, and they want us to turn it around and show the dissociation of water. So we turn the chemical equation around. What do we do with delta H? We change its sign. So if a reaction is exothermic in one direction, like this one, it will be endothermic in the opposite direction. A little bit more of the manipulations here on this example. We've got this thermochemical equation here, and they want us to calculate the delta H values for these different thermochemical equations written here. So part A is just the same reaction as the one given in the problem, and so the delta H value is the same. For part B, you can see that the coefficients have been multiplied by a factor of 2, so you do the exact same thing to the delta H value. In part C, you take the original equation and you reverse it, so you change the sign of delta H. For part D, you've reversed the chemical equation and you've multiplied by 2, and so that gives you the -412 kilojoules here. And in the follow-up problem, which of these reactions is the most exothermic? It would be part D, because it has the largest negative value for delta H. This example problem is meant to remind you that you can use the delta H values in stoichiometric problems. And so here we have this reaction involving the formation of ammonia, and they want to know how much heat would be evolved if you produced 9.07 times 10 to the 5th grams of ammonia. That's quite a large amount of ammonia, so that would be about 907 kilograms. It's an exothermic reaction, and so what we have to do here is we have to convert the grams of ammonia to moles of ammonia, and then once we're at the mole level, we can convert straight to the energy. So taking the starting value, dividing by the molar mass of ammonia, which is about 17, and then we use the stoichiometric ratio for every 2 moles of ammonia that are produced, we're going to produce 91.8 kilojoules of heat. And so I've included that conversion factor here. You run the numbers and you get this value. And this is a large amount of heat because we've made quite a large amount of ammonia. In this slide and the ones that follow, we'll be talking about Hess's law of heat summation, which tells us that the enthalpy change for an overall reaction, which involves multiple steps, is just a sum of the enthalpy changes for the individual steps. So imagine that step 1 here has a delta H value, delta H1. Step 2 has a delta H value of delta H2. The delta H for the overall reaction from going from A plus B to E plus F is just a sum of the two steps. So you add the two chemical equations together to give you the overall chemical equation. You do the exact same thing to the delta H values to get the overall delta H. So this is the Hess's law, and we'll see some examples of that as we go. Here's one that I've worked out on the slide for you. Here's a kind of a practical example of Hess's law. So suppose that you're interested in the partial combustion of graphite. So you want to know what happens when you burn graphite to produce carbon monoxide. What's the delta H value for this reaction? Well, the trouble with this question is that you can't actually do this reaction in the lab. You're never going to get just carbon monoxide coming out of graphite. Normally what you're going to get is CO2. You might get some CO, but if you keep burning the CO, then you're going to convert all of the product to CO2. So this reaction here can be carried out experimentally. This one can't be. Still, you might want to know what the delta H is. So anyway, you carry out the full, complete combustion of graphite and measure its delta H value. And then you take a sample of purified carbon monoxide and you burn it to completion to give you CO2. You can do that experiment in the lab as well, and that gives you this delta H value. The trick here is how to combine these two numbers to give you the delta H value that you want. And you use Hess's law to do this. So the idea is that you want to construct the unknown reaction from the known reactions. Okay, and I do this by inspection. So here's how I do it. I'm trying to build reaction 1, this reaction here. And so what I do is I look at the reactants and I see, what reactant do I have here, or do I want? I want carbon graphite. And so I look at my known reactions for carbon graphite and I see it here in reaction 2. It is on the reactant side, which is good, that's where I want it, but I want a stoichiometric factor of 2 in front. And in the known reaction, I only have a stoichiometric factor of 1. So what I'm going to do is I'm going to say that reaction 1 is going to be 2 times reaction 2. And that's going to give me the graphite that I want with the correct stoichiometric coefficient. But we're not done yet. We also need to make sure that we get the other species that we want. So I look at the next reactant, O2. That guy is kind of complicated. I see that it's in both reaction 2 and reaction 3. That's my signal to ignore O2. So skip it entirely and move on to the next species in the reaction. That's the carbon monoxide in this case. Right? I want 2 moles of carbon monoxide on the product side. What do I have? I've got 2 moles of carbon monoxide, that's good, but it's on the wrong side of the reaction. I want it on the product side. So what I need to do is I need to turn this reaction around. So I need to flip it. So I'm going to take minus reaction 3, and that's going to give me the carbon monoxide in the right place with the right stoichiometric coefficient. And if you carry out these operations on these reactions, you indeed will produce this reaction here. Then, to get the delta H value, you do the exact same operations, but on these delta H's. So the delta H for reaction 1 will be 2 times the delta H for reaction 2 minus the delta H for reaction 3. You plug in the numbers, and it gives you the value of the delta H that you want. Okay, so this is an example of how you can use Hess's law to solve a problem. Here's a slightly more complicated version of the same problem. We have this formation reaction that we're interested in. We want to know what's the delta H for producing tungsten carbide from tungsten metal and graphite. Okay, maybe this experiment is hard to do, but we can do these other experiments here where we can combust tungsten. We can combust graphite, we can combust tungsten carbide, and we can measure these delta H values. The trick is how to calculate this delta H that is unknown from these known delta H values. We're going to label these reaction 1, 2, 3, and 4. So we want to build reaction 1 in terms of reactions 2, 3, and 4. So I see that I've got 1 mole of tungsten on the reactant side in my target reaction. I look in my known reactions. Where do I find the tungsten? It's here in reaction 2. It is on the reactant side, which is good, but it has the incorrect stoichiometric coefficient. I want a coefficient of 1, but this one has a stoichiometric coefficient of 2. So what I'm going to do is I'm going to take this chemical equation and I'm going to divide it by 2. And that's going to give me the right amount of tungsten on the correct side of the reaction. What's up next? Graphite. Okay, I want 1 mole of graphite on the reactant side. That's what I find here in reaction 3, 1 mole of graphite. So I'm just going to simply add in reaction 3. The last species that I want is the tungsten carbide. I want 1 mole on the product side. My reaction here has 2 moles on the reactant side, so I need to flip this around. So I'm going to multiply by a negative sign, and then I also need to divide it by 2 so that I have the correct stoichiometric coefficient on the product side. And it looks like I made a typo here. This should say 1/2. That's too bad. So it should be minus 1/2 times reaction 4, and I probably did make that error in the calculation, so this number is probably no good. I'll leave it as an exercise for you to correct that factor here and to get the correct number as well. Let's see, the next topic, standard states. So we use all sorts of data tables when we're doing thermochemical problems. And one of the tricky parts about thermodynamics is that all of the quantities that we're talking about, delta U, delta H, later we'll talk about delta S and delta G, these quantities are temperature dependent and they're also pressure dependent. And so you need to tabulate the thermochemical data at a given temperature and pressure. And that's what standard state is about. So this is the recognized pressure value for which thermodynamic quantities will be tabulated. For our purposes, that will be 1 atmosphere pressure. And although there is no official standard state temperature, it needs to be a fixed temperature. And the most commonly used temperature is 25 degrees Celsius or 298 Kelvin. And so when we calculate or when we measure a delta H under standard state conditions, we use a little degree symbol here. I'm just going to call it a circle to indicate that we're talking about a delta H value that has been evaluated under standard state conditions. Typically, though, when using this notation, when using the little circle, we switch from an extensive quantity to an intensive one. So by convention, a delta H with a circle is usually regarded as an intensive quantity expressed as kilojoules per mole of reaction. And you have to be careful here because many textbooks are somewhat sloppy with the units, including our own. Sometimes they're talking about extensive, other times they're talking about intensive. You just have to be very careful about your units. I try to be careful as well, and so whenever I mean the intensive version, I'll usually use the circle, and if I'm talking about the extensive one, I won't use the circle. Anyway, you can usually figure out what's going on from the context of the problem. A related topic to the idea of standard state is the notion of a reference form of an element. Okay, this refers to the most stable phase and allotrope at standard state conditions. So we all know that elements are substances that are composed of only one type of atom, and you may recall from Chem 120 the idea of an allotrope, that is, elements come in different forms. So for example, oxygen, you could have monoatomic oxygen gas. You can also have diatomic oxygen gas. And this triatomic oxygen gas is called ozone. These are all allotropes of oxygen. And under standard state conditions, only one of them is the most stable. and that is the diatomic form of oxygen. Likewise, carbon comes in many forms. Graphite and diamond are two examples of solid carbon, and the most stable one under standard state conditions is the graphite. So graphite is the reference form of carbon. Here I've listed the common reference forms that general chemistry students need to know about. So you need to know that diatomic hydrogen gas is the reference form of hydrogen, diatomic nitrogen gas for nitrogen, diatomic oxygen gas for oxygen, diatomic fluorine, diatomic chlorine. For bromine, it's diatomic, but it's the liquid phase that is the reference form. For diatomic iodine, the solid phase is the reference form. And then basically every chemistry student needs to know that graphite is the reference form of carbon. Here's some other examples that aren't as important for you to commit to memory. But you're basically expected to know this, to know these different reference forms for the common main group elements. Another idea that's important in thermochemistry is the idea of a formation reaction. And if the formation reaction is carried out under standard state conditions, it's called the standard enthalpy of formation. And so we use this subscript F to denote a formation reaction. What I'd like you to recognize here is what are the characteristics of a formation reaction. A formation reaction involves only 1 mole of a single product, a compound, typically. So there is a formation reaction for water vapor. There is a formation reaction for carbon dioxide. In this case, we're looking at the formation reaction for methanol. Every compound has its own formation reaction. And on the product side, there should be only 1 mole of that compound and nothing else. On the reactant side, what you have are the elements that make up that compound in their reference form. Okay? So for water vapor, the elements that make up water vapor are hydrogen and oxygen. The reference form of hydrogen is H2. The reference form of oxygen is O2. In order to get the stoichiometry correct, you need to put a 1/2 here in front of the O2. And you should not get rid of that fraction. Okay? So formation reactions can and often should have fractions in them. Here's the enthalpy of formation for water vapor. The formation reaction for CO2, you've got carbon. Graphite is the reference form of carbon. Again, diatomic O2 is the reference form for oxygen. And so this is the formation reaction for CO2 with its corresponding standard enthalpy of formation. Here's one for methanol. Methanol is a little bit more interesting. You've got carbon, graphite. You've got 4 hydrogens on this side, and so you're going to have 2 diatomic hydrogens over here, only 1 oxygen, so you need 1/2 mole of diatomic oxygen gas. Each of the elements in their reference form for standard state conditions. These standard enthalpies of formation, notice the circle, they are intensive quantities in the sense that they are kilojoules per mole. One other point to note is that the enthalpy of formation by definition for an element in its reference form would be 0. Okay, so the formation reaction for O2 gas would be O2, 1 mole of O2 on the product side, and then oxygen in its elemental reference form on the left-hand side, which is O2. So you would have O2 going to O2. Since the reactants and products are the same, the enthalpy of formation would be 0. Here is an application of formation reactions. So this is the most important application of formation reactions. So suppose you're interested in the standard enthalpy of a reaction for some reactants going to products. Here's what you can do. Imagine taking the reactants and then decomposing them into their elements. Then recombining those elements to make the products. So we have this hypothetical two-step reaction scheme. The first step is the reverse of a formation reaction. You're going from the reactants to the elements. And so the enthalpy of reaction for this first step would be a sum over all of the enthalpies of formation multiplied by the stoichiometric coefficients in the reactants multiplied by -1. Okay, and it's -1 because this is the formation reaction in reverse. The second step, the second conceptual step, is the forward direction of a formation reaction. Here we're forming the products. And so the enthalpy of reaction for this second step is a sum over the enthalpies of formation for all of the products multiplied by their stoichiometric coefficients in the products. Hess's law tells us to get the overall delta H, what we need to do is add up the delta H of the two steps. And so we wind up with this products minus reactants formula. So you can use this idea and tables of enthalpies of formation to calculate the enthalpy of reaction for any given reaction of interest. And so here's an example of that. So we're being asked to calculate the standard enthalpy of reaction for this reaction here. And what we do is we go to our table of thermodynamic quantities. So there's an appendix in your textbook that lists various thermodynamic quantities for all of these different compounds. You go look up all of those numbers. Here's the ones that we need. And then we use that products minus reactants approach to calculate the delta H for this reaction. And so here's how I do that. So the delta H that I want to calculate, I'm going to read the reaction, products, and then I'm going to subtract the delta H of formations for the reactants. So starting with the nitrogen monoxide, I'll take 4 times the enthalpy of formation for nitrogen monoxide. And that's going to be this middle number here, the 90.29. Then I'm going to add to that the enthalpy of formation for the water vapor. But I'm going to multiply it by the stoichiometric coefficient of 6. So plus 6 times the enthalpy of formation of water. Now that I've exhausted all of my products, I'm going to start in on the reactants. But I'm going to use minus signs for each reactant. So it's going to be minus 4 times the enthalpy of formation for ammonia. And then conceptually at least, it'll be minus 5 times the enthalpy of formation for O2. And so you just look these numbers up and you substitute them in. Note that this oxygen, diatomic oxygen, this is the reference form for oxygen. And so its enthalpy of formation is by definition 0. And so you're not going to find an enthalpy of formation for oxygen in your table of thermodynamic quantities. You just need to know that it's 0. So you substitute these numbers in, you substitute in 0 for the enthalpy of formation of the O2, and you should get this number. Here it looks like I'm leaving this as an exercise for you guys to practice. You'll need to use these values and use the products minus reactants approach to calculate the delta H for this reaction. Okay, so I'm going to stop this video right here.